Recording this, hopefully. F5. I'm trying a totally new technology today, hoping it will work. So how is everyone? How is homework 2 going? Good? I'm seeing a lot of activity on discussion boards. That's good. There's a lot of good discussion going on. I believe everybody is now grasping the gravity of how powerful of a tool the discussion board can be. Please continue using it, okay? The more you use it, the more powerful it becomes. And actually, I'm even going to recommend towards the end of the lecture, you can start taking printouts of your favorite parts. Keep them as lecture notes. Okay. All right. How many people know what it is that what you're looking at? Let's start with the traditional question of the day. Yes.
It's obviously a James Bond car, so therefore it's a tank because it's got a cannon under the hood.
It's not James Bond. Good guess though. Yes. Amphicar. Yeah, somebody knew. When were you born? 94. Respect. Because this what you're looking at is a 1961 Das Amphicar. It's a German make. It's a real car, not photoshopped. They used to call it the Splashy. All right. Now, it's the coolest thing ever. Why don't we see more of them today? Not practical? Well, why not? You can swim to work and drive to work at the same time. I won't traffic. Might be a cool idea if you ask me.
Regulations or something.
What regulations?
Also being a boat.
You can just drive away from regulations. I have a machine shop in my bedroom. I have a 5-axis machine shop, and when there's only 2 places in the state of Iowa who have that, the Vermeer company and myself. And when I was talking to company executives, they were like, "How did you get past the regulations?" I was like, "What regulations?" Exactly. The company was founded in 1961. They had a great idea, and they inventoried for 20,000 car sales within 1 year. 20,000. They ended up selling less than a fraction % of that, just because of one article Time magazine published. And they called it, well, on the land, it drives like the Queen Mary. On the sea, it floats like a car, or doesn't. They called it the vehicle that's going to revolutionize drowning, because the car required a bilge pump to get the water out. So if you open the door, I double dare you. So if you ran out of gas on the water, you knew where you were going, down. Now what's the point of all this? What I'm about to tell you, some of you will not like. It's okay, let me be the devil's advocate. Hate me for it if you must. The day will come that you will understand and appreciate it. I have your best interest here. Let's skip this whole instructor-student thing. Let me talk to you like a brother, okay? I have a brother about your age. Computer engineer too, so I'm setting that example, I guess. A lot of you have been coming to me this week asking, "Dr. Chilek, can I skip this lecture because I have band practice? Dr. Chilek, can I skip this lecture because I have dance practice? Because I'm going to go to see my Chinese studies. Because I have, football." The Amphicar, in engineering school, if you are going to make a well-rounded person out of yourself, that is where you're headed. your career is going to become, or could become, the amphichord. Okay? I really like this one with the harp. Do people have harp in the marching band? Yeah, I think you should. Now, when I show this to people, as students I talk to, especially Omega, you know who you are. Omega said, what do you know about music anyway to judge my decisions? Just say, you're a typical engineer, I mean, no appreciation for art. Dude, that hurts. Engineering is art, all right? Look at the Boeing 747. That's art, that's mechanical wizardry. Engineering is the art form of science. But prejudice is said to be the ink the entire history is written in. Because what Omega didn't know is maybe I know a thing or two about music. The reason I'm trying to warn you is because I used to be one of you. I guess now you know who the mystery guitarist was the first day when I was trying to teach you analog and digital. And it wasn't just a side project, guys. I made 2 albums out of a 40-hour-a-week engineering career as a side to it. Okay. The problem is, I noticed that I failed at becoming both Tesla and Beethoven at the same time. It's not a question of if, but when. Everyone who has a second curricular activity that is orthogonal, not married to, at least not fully, to what you are trying to specialize in, the choice you'll have to make. And I chose Tesla. Long ago. That picture you saw is very old. Okay? Now I'm not going to tell you which side to choose. I already chose the dark side. I think that's pretty obvious. Just that someday time will come that you will have to make a choice. The day I graduated, I could play Asturias Leyenda. How many people know Asturias Leyenda? Not surprisingly, there are 6 levels of guitar specialty if you go to music school. I was a level 5, beginning of level 5, self-taught. And I had an engineering degree. And I was feeling like, you know, a dog with 2 tails. I'm like, I can play the guitar just good, and I'm a computer engineer. Well, turns out, people who appreciated my music did not appreciate my engineering. People who appreciated my engineering did not appreciate my music. And it had to be either or. I mean, I couldn't go to my landlord, Kevin, here's a serenade for you. This is Asturias Leyenda by Segovia. Didn't work. He actually wanted money, right? So life is cruel. Sorry about it. But here's the point. People, every time you skip my class, you are choosing a side a little bit. 10 years from today, who will you be? And will you like that person? Think about it when you are making that choice. I already know you need to go to band practice and whatnot, whatever else activities you do. The university already tells me about it, all right? So before you even come to me, I know that you might go. But I always have this little hope that, you know, maybe one student will say, well, let's do engineering today. If you came to me with something like, Dr. Chek, I have a ham radio club. I need to skip class on Friday because we will try to send a microsatellite, just for the fun of it. I will take the class on a field trip, come to wherever you're going. And I have done in the past. I have taken 85 students out of the classroom, took them to a cornfield to watch a drone fly. All right? So, I will do that if one of you come with that type of excuse. All right. So, now that I have demotivated you, maybe I have broken your heart. I'm sorry. I'm doing it all in good intention. I have your best interest. Now we will resume your regularly scheduled lecture with the expensive electric pen. All right. So what we were doing last lecture, we were talking about the canonical form. So far, I'm seeing everybody is understanding canonical form. You are doing homework about it. That is good. So what was canonical form? Well, canonical form was a sweet spot between random logic and the absolute minimal form of a circuit. Correct? Because we discussed there could be infinite number of circuits that could do the exact same thing, not necessarily for the better. If you look at the chair out here, maybe it would make a nice rocking chair. I don't know. That thing looks creepy to me. So why should we simplify a design? Makes it more sustainable, efficient, cheaper, faster, quieter. I can name you a million reasons. From random logic, when we are at random logic, you're going to canonical form from that. We do that through min-terms and max terms, right? So min-terms and max terms give us that standardized point to begin with. And after that, if we want to further manipulate it, further minimize, we can use algebraic manipulation. Now, algebraic manipulation is what most of you are having pains about, teething troubles, as I call them, which is normal. Don't panic. I'm not going to hold you accountable for those. I'm just trying to make a point here with these homeworks that out there real engineers don't do it with algebraic manipulation. But if I don't show you a little bit of that, a little bit of taste of that, you will never appreciate it. Of the tools that are about to come. Okay. So how do we simplify a given canonical form function? Now what I'm going to do next, I mean, if you were not listening up to this point, this is the point where you should start listening, okay? Because it's going to get important. When we simplify a canonical function, or any other Boolean function for that matter, it can be another Boolean function that we can simplify. It doesn't necessarily have to be in canonical form for us to simplify it. Is that clear to you? Yes, I can have something that is not in canonical form, bigger than canonical form perhaps. I can still start simplifying it, but canonical form kind of makes sense, and we already talked about why. Now, unfortunately, I mean, a lot of you have been coming to me and asking, what is the key to doing this? Okay? It's kind of like asking, what is the key to getting rich? There's no single key. The key is different for every application. Unfortunately, that's the case here, and I know that's not fair, but I'll try to help you out a little bit. Now, just like canonical form uniquely identifies a circuit, we also have a system that uniquely identifies a minimization of a given circuit. We call it a Karma map. So in fact, there are maps to where you're trying to go. You don't have the map right now. I could give you maps first, but if I did that, it would be very confusing because those maps are in hyperbolic space. You are all used to thinking in Cartesian space. Nobody taught you hyperbolic space so far, except perhaps your friend who knows about the amphicar. You probably also know about the hyperbola. Is that correct? Yes or no? Why are you so quiet? He's all like, so let's do this one. Actually, not this one. Not this one. I have another one for you. This is the one I wanted to do. Okay. So let me write it. AB plus, can you see that?
Yes.
AB prime. What am I doing? Oh, okay, maybe I shouldn't put my palm on it. Sorry, I'm still trying to get used to this thing myself. AB plus AB prime plus A prime B. That's what it was, right? So AB plus AB prime plus A prime B. All right. So here's my first step. That kind of looks like a 2, but that's actually 1. By the fourth postulate, I can do this. Can everybody see what I did and why I did that? Look at this. There's a B and a B prime conveniently sitting there together, begging to be grouped under A. So that was easy. Let's do that. What should mean by second step? Now this, I know, is a situation I should avoid. Is that correct? So that puts me into my second step where this becomes A multiplied by 1, which is just the same thing, A itself, plus A prime B. Now it's looking more friendly, doesn't it? Because that's also equal to A multiplied by A prime B. So it brought me to this point. What can I do now? I mean, I can't really group it. I have an A and A prime on opposite ends of an order. Yes?
There's a property for that.
There's a property for that. We could do that. We could do the 16A. How about this? How about this? Now I'm going to go against the belief, and I will actually add a gate rather than trying to remove the gates. Let's try this. Let's try something like this. What if let me do this with a different color. Where's my different colors? Okay, there. Can I do this?
Yeah.
Without affecting the circuit at all? You remember the whole absorptions and VCCs and grounds that do not affect the circuit, right? So let's do that. I'm actually going to go ahead and pick a darker color. Not all of us have the gift of eagle vision. I am one of those people, so I hear you. Mine is actually far-sighted, so if you get close to me, I don't see who you are. But the farther you sit from me, the people in the back, I actually... I can read your cell phone screen from you. So I know what you're texting. Maybe. Then this becomes the fourth step. So my fifth step, because I added the 0 here. Let's try doing this. A plus A prime B plus, how about that? A multiplied by C prime. Now, inserting a 0 here did not have any effect on the circuit. I already knew that. So why not represent that 0 with a gate? An AND gate. AND gate is cheap, at least right now. I'll make it more expensive in the exam. In the class, they're pretty cheap. Buy one, get one free. Okay, actually in the exam, I'll make the NAND gates cheaper, and I'll tell you why. Okay? Did everyone understand how I went from 0 to AA prime? And the sixth step would be A plus. Now I can do a B parentheses. It allows me to do A plus A prime. This is also the fourth postulate. When you're solving something like this, it helps big time if you have those postulates and theorems printed out, maybe on a cheat sheet or a study card, whatever you people call it. Yes? Why?
So if you distribute that, you get BA plus BA not.
Now, you need to remember, there are multiple ways of doing it. What I'm teaching you is not the God's given way. This is just one way of minimizing. Okay? So you will see, this is the both beauty and the curse of it. Which method should I pick? Right? Can you see it now?
What is postulate 4? Like, is there some sort of magic in there that lets you...
What is postulate 4? Yes. Is there some sort of magic in there? There is some sort of magic in there. The magic is the postulates work in electrical terms. They don't necessarily make full algebraic sense at all times. Okay? How many people recall that? When we were trying to add, let's say, a to 0. I'm sorry, a to 1. It gives us a. Let me go through this. We'll come back to it, okay? I'll pick a different color. This reduces to 1. A plus its prime. So because whatever A is, it will be going through an OR gate. So if this is a 0, this will have to be a 1. If this is a 1, this will have to be a 0. So I know my OR gate in there has to give me 1 as an output. Hence, this becomes A plus B multiplied by 1, reduces to A plus B. Now, when you go home with this, I'll give you these slides, don't worry, the annotations on them, everything. Try to work it out yourself. And you will see, you might get to A plus B through multiple different ways. Some of them will get you close to A plus B, and it's going to have a third term here. And that third term is going to be a redundant gate that doesn't have effect on the circuit. It's a little bit of intuition, a little bit of electric wizardry here. You should try to think in parallel, both what's happening in algebra and what's happening in electrical circuit equivalence as you draw this, as you solve this. Now, at this time, it may be difficult to form the mental picture, but as we progress in the course, it'll become second nature. What I recommend you do when you're studying it is for each step, draw the circuit. For each step, draw the circuit. Now, you might be going, well, we draw circuits, they look like spaghetti. I know. All the circuits I have seen. I'm going to show you a tool to do that. That will make it very easy. Okay? So it's not going to be a chore anymore. It's actually even going to be fun. Okay? All right. All right. So how do I erase with this thing? How about this one? Now, is it a canonical form? Can you say? Not really. I mean, this part here looks canonical-ish, but then I have this B here altering the whole business. Like I said, the previous equation we solved started from a canonical form of a simple circuit. This one is a canonical form with some redundant gate and terms, inputs if you will, added to it to demonstrate. Now you can start with a Boolean function of really any size actually. Okay. And then if you try to become a PhD student at Iowa State in the qualifier exams, they will give you a Boolean function. Okay. I'll tell you that question right now. That Boolean function is going to have infinite number of XOR elements in it. So an infinitely long function, and they will ask you to simplify it. If you actually try to do it, you're not going to do it. Won't finish. But it actually, well, it is infinite, but it ends up becoming a very simple circuit if you know how to do the Shannon's extension theorem, which is something I have not taught you yet, but when I do, it will make a lot of sense. So this question stems from that, but it's not necessarily as cruel. This one is still undergraduate level after all. So here's my first step. Now what can I do? Now does it look more friendly? It does. It's more canonical-ish now. That sounds like a bad word, canonical-ish. It's like a ticklish. Anything that ends with ish, anyway. Then what can I do? I'm still keeping my plus C on the side. Now, from high school and from the courses you have taken so far, you are used to thinking in mathematics. This is where that stops. When I look at that plus C in the end, I don't think of it as a variable anymore. I think of it as an OR gate with a cable coming out of it. I have a dangling OR gate. That's the way you should think. And that's why it's helpful to draw the circuits. Okay? This clearly becomes 1. This becomes 1. So I brought it into a form that reduces to a multiplication with a 1. It's making it a redundant AND gate and then turning into a buffer and then becoming the variable itself, really. A buffer gate is the variable itself. And then C. And then the rest is really obvious. Plus C. So, that. This was my circuit. Something I could have done with a single. Now, I hope you are seeing it somewhat follows a pattern, especially if the circuit is small and well structured. There are only so many different ways it can fold and collapse onto each other without destroying its function. But once the circuits get more and more and more complicated, once we start talking about 1,000 gates, 10,000, 100,000, a million gates is not out of the question. Your typical laptop is going to have a couple million easy. And that's a low-end laptop. That becomes a big problem. Okay? Then before, yes?
Where did the C go in the first block? You had three blocks. APA plus BC. Where did C go?
Absorb.
Second.
Signal absorption. How many people remember absorption? Okay. When you are thinking about the theorems and postulates, think about them like amoebas, all right? Those microbes. Or lymphocytes, the white blood cells. They have capability to eat each other. They have capability to separate from each other. They have capability to absorb signals, not let them out, send them to ground. They have capability to create signals out of thin air. Now that sounds like it doesn't make sense. How can a gate create a signal out of thin air? It can. Because if you remember, first week I was talking about the gates having their own power source. So a gate sitting there like that, innocently, an OR gate like this one, is connected to power. Okay? So even if you let its inputs dangle, or its output dangle, it can still create a signal for you. Would that be a signal you want? Well, depends. More often than not. Okay. All right. In case the pen didn't work, I put the nicely typed versions on the slide. So you can work them out yourself. But I highly suggest, because I'm going to move on from algebraic manipulation, all right? Starting with your third homework, we will start going into more advanced topics where you will have to bring in more advanced tools to do this. And every time you see an equal sign here, draw a circuit. Okay? Draw a circuit and take a look at it. When you look at it at circuit level, it will start making a whole lot more sense. Now, let me take a little break here, make just a little diversion, and talk about habits. Last lecture, we made a little mention of hazards. I showed you that if you have multiple circuits that do the exact same thing, they're identical of each other. But one of them is redundant in such a way that one of its gates may have a manufacturing defect. This happens in real life. In your textbook, all the gates are the same. If you have a box containing 1 million AND gates, they're all the same AND gate. I work for the Grundig company. It's a big electronics manufacturer in Europe. They make a television set every 2 seconds in the factory. They work 24 hours, 3 shifts. Those AND gates, they come by the truck, right? If they dump them in, out of 1,000 TVs they make, about 10 of them will have an issue. You know how they used to find it? The TV would come to a station, a guy with a hammer would bang it, see if it still ran. See if he could work the gates loose. That was his job, hammering televisions. I mean, if you're going to complain about your job. So out of that bin, the manufacturer actually told you a mean time between failure figure and a probability of a gate being bad figure. There are bad gates, meaning they had a manufacturing defect, or they got dust in them, or they have longer. They might respond longer than ordinary gates that you expect, or they might respond quicker. It's kind of like you go buy a 3 amp fuse. Turns out it was a 3 amp fuse labeled, but it was actually a 2 amp fuse, something like that. Or worse, it's a 5 amp fuse. Okay? So the expensive circuit will burn to protect the fuse. Huh? It happens. Perfect gates never cause hazards. Equal gates never cause hazards, so you're not going to find perfect gates in real life. Life is cruel. Get used to it, like I have been saying at the beginning of lecture. I'm leaving this slide in. When you find a job at Intel, Xilinx, Boeing, wherever it is you might go, you put the appropriate present progressive verb here, because every circuit is out there to hate you. They never work. That's the motto of engineering. It never works. If it did work, they would not need you. The reason they will hire you is because you know how to make it work. Well, at least you will after I teach you how to make it work, hopefully. Okay? But if you go at this with the assumption that all gates are the same, then you remember the body bag? Yeah? You know what happens. Let's take a look at this. Now, before I continue, do you like this drawing? Like it any better? Do you want to be able to do these? That's coming, okay? I will give you a tool to do that. It's a lot more fun than Quartus. I'll try to implement it in Blackboard. If I cannot, I'll give you another form where you can use it as a non-install form. We'll talk about that. But let's do the boring stuff, get it out of the way first. Let's consider an imperfect circuit. What's an imperfect circuit? An imperfect circuit means that the gates that I have, although they are equivalent gates, one of them has a manufacturing defect. Now, I have three inputs, x1, x2, and x3. That's my function. x1 multiplied by x2 plus x1 prime multiplied by x3. Now, in this circuit, if all gates were to perform and function normally, let me get my highlighter for this. If no delays were to occur, the gates would function normally. Then when I change my state of x1 from 1 to 0, what would the circuit do? Let's say they're all 1 right now. This red means it's 1, okay? What happens if I turn this off? What happens if x1 is turned off? What happens to the output? You sound like this. Still 1, yeah. Good. Speak louder, okay? So this is the functional states of the circuit. x1 is a term whose change is not supposed to affect the circuit. If all gates, in fact, responded instantly or at the same propagation meter. Well, let me add a little challenge to you here. See this little NOT gate? Inverter gate is the cheapest gate out there. They buy them by bulk. Yes. Buffer. Oh yeah, absolutely. Buffer gate, definitely. Buffer gate counts too. But for the sake of argument, it's more difficult to show this phenomenon with a buffer gate if you don't have an oscilloscope. With an inverter gate, you can look at it by the signal. Now, how about this? Let's take a look at it like this. Let's say my AND gate is defective. I'm sorry, my NOT gate is defective. So it's taking a delay to respond, which means that I can have a state where when I set my x1 from 1 to 0, my output remains 0 until this gate decides to respond, and then this gate propagates that, and then that gate propagates that, and the output comes. Now, why is this a problem? Well, what if this circuit was controlling the cooling pumps in a nuclear reactor, let's say? And you are making your calculations based on that the system will trip instantly, but it takes, chills out a little bit. And then you have another turnover. Okay? So this is what I was talking about when I said you can kill someone with it. You can literally kill someone with it. Timing is the single most difficult part of computer engineering, time synchronization of circuits. When you go to 381, if you take it from me, I don't know, depends. Because if you don't like this course, clearly I'll be selling lemons, so you'll be taking it from someone else. CPUs have reached speeds that are so high, the speed of light is not fast enough to get from one end of the chip to the other end in time. Okay, we will talk about clock synchronization as we come to that topic towards the end of the lecture. But you always have to be mindful of it. So how do we fix it? What's a good way to fix it? Adding a redundant loop, a redundant circuit can actually eliminate that hazard. Let me highlight that for you. I have my first original circuit here. This is original. That one is gone. You'll see it, okay? I'll show it to you. Don't go. And I have another circuit right here. This is the second one. That is a redundant circuit. Now, a few of you have come to my office hour just before this lecture. Actually, one of you asked a similar question: why the consensus theorem is working? Thereby adding one redundant gate into the circuit. A gate that would normally not be needed, a gate that would make it waste power, ensures that even if this gate is defective, you see there's only a single NOT gate. I'm not adding a redundant NOT gate. I still have a defective gate. This is defective gate is still there. But my redundant gate is now ensuring the circuit is responding in a timely manner. Okay. This is the reason why when you are doing algebraic manipulations, sometimes you actually have to insert stuff. It makes sense to start making a circuit bigger, more complicated, than to be able to reduce it to something else more meaningful. Does that make sense? Now that's the slide you were so excited about. I have a toy for doing all this. It's called Hades, named after the Greek god of underworld. Well, I know that's a goddess, but that depends on which Greek you listen to. All right. So let's give Hades a try. And after seeing Hades, you will hate me. Don't hate me. If I gave you Hades the first day, you would not learn any of this. All right. So let me get out of PowerPoint. Keep, of course. It's got a pretty simplistic interface to it, okay? I don't know how well you can see what's happening here, but let me try to walk you through. Let's give it a fine grid, okay? At the bottom part, you have your time. You can run the circuit from anywhere from a picosecond all the way to days. So how long do you want to simulate? Basically, you set it at, right now it's 100 nanoseconds. Let me go set that to a little bit more meaningful number, and I'm going to make that 100, I don't know, seconds, okay? It entirely works by right click. So you come on this screen, you do a right click, okay? And it pops up this menu. Let me go to Create, I/O, and let's start by creating a switch, right? Right there. How about 2 switches? You left click to put it down. Now let's create gates. Let's pick a gate. How about AND gate? Does that work? Here's your AND gate. And you want that bigger? How's that? That nice? Now if you want to make a connection from this point, you just click on it. Oops. You have to cancel the gate mode first. I'm still trying to get used to the touchpad on this thing, so bear with me here. You left click and you drag a cable. Left click and drag a cable. Okay. Let's add some sort of an output to my gate so I can see it. I will create I/O LED. Okay, so here's an LED. And then I'm going to do a left click connect. All right, so let me start running the circuit. Initially, when it's blue, blue is an undefined state. Let me turn it off. When it's turned off, all cables are gray. Let's try the AND gate. Give it a one there, and the AND gate comes on. How's that? Now that's a homework that rocks. Your TAs are gonna love it. I will certainly appreciate it. And you will take this tool, and you will have no excuse not to go back to the minimizations and draw the circuits now. So easy. So easy. Once you draw a circuit, you can save it. You can load it just like any file. There are some that I have drawn earlier. Let me open one of them.
Can you save it as a JPEG as well?
Yes, you can save it as a JPEG. You can export it as a picture if you want, or you can just take a screenshot if you want. Both are acceptable options, okay? let me open the basic gates. Here's your basic gates. The buffer gate, on, off, the inverter, on, off, okay, the NAND gate, right there, you can play with it, the NOR gate, OR gate, okay. Let's try the De Morgan's theorem. Don't worry, I'm going to give you these files to play with, okay. Here's the De Morgan's theorem. You already know what De Morgan is. You can actually visually verify it here. But that's boring. Let's do something a little bit more interesting. How about making a fan gate? So I asked you to perform an AND function of 16 inputs, but I'm only giving you 3 input AND gates. This is how you do it. You perform a fan gate. And a fan gate will only give you output if it's made of AND gates, if all the inputs are 1, right? Right there. And the opposite of this function would actually be the magneto function we did. Any of them would have to be 1 for it to work. This is sort of the same. But that one is a NOR, so it's doing the opposite. Okay? Hades is extremely powerful. Now going back to the hazards picture. Now this one's important. This bit is important. Watch it. Once you right-click a gate and you go edit, it tells you, it asks you if the gate is defective. You can say that this gate has propagation delay of this many seconds or milliseconds. Right now I set this to 0.3 seconds, which is light years actually in gate terms, so that you can see it. There's my AND gate and output. Let's try how this hazard works. See what happens when I click my input in A. Did you see that? It's blinking. Turns on and then off. Because of the gate's delay. How about this one right here on the right side, B? When I turn it on and off, I'm not getting that instantaneous response. How about if I have a cascade of these like this? I have what, 5 of them? Right here. 5 cascaded NOT gates. Let's take a look. Take a look what happens. I click on this. Whoops. Lights went off. I'm sorry. Your power factory just blew up. That's what it is. Life is cruel. Hazards, they are going to be out there. You need to anticipate them. Okay? And if your application calls for it, you either have to use the most expensive NOT gate, which can still be defective, by the way. All right? Just because it's expensive doesn't mean it won't be defective. Let's take a look at this one. This is a collection of NAND gates. It's called a NAND chain hazard. See, it's not supposed to blink at me like that. It almost looks like it's giving you a pattern. It actually isn't. It's randomly oscillating. It's trying to settle. You're clearly not getting the function you have expected. All right, here's another one. I'm going through these fast. I just want to show you this in this lecture. I'll let you play with it yourself. Okay? So don't worry if it feels like it's not making sense. It will. Now, does this one look familiar now? Look at this. This is one of the problems we simplified. A and B. 2 circuits. The top one, A plus B, the simplified form. The bottom, AB, AB prime, A prime. 2 different circuits doing the identical thing. And we can test that when both inputs are 1, both outputs are 1. A is 0, B is 1, both outputs are 1. When they are both 0, both outputs are 0. When A is 1, both outputs are 1. So, which is actually painfully obvious because the simplified version of that function was A plus B. So that's an OR gate. But something you could have done through an OR gate, now that you are using what? 1, 2, 5, 6 gates to do. And your 6th gate is actually a 3-input gate, so it's a fan gate, meaning it has more gates. Now the last thing I'm going to show you is, I don't know if I can get it to work, so give me a second here. Okay, it's not going to work, but hey, this was supposed to show you a text here, so it was doing ASCII text process. I'll get you the working version of this next slide. Hades is extremely powerful. It can simulate anything from a simple AND gate all the way to an Intel CPU. All right, so don't underestimate it. We will be using Hades for the rest of the course when we are trying to visualize what algebra is trying to tell us in terms, all right? Okay. I will put this on Blackboard. I'll tell you how to download it and how to run it and whatnot, okay?
Hey, I am having a problem with homework,
Yes.
and the problem I'm having is that number 5